Hey everyone, and welcome back to the channel. Today is March 20th, and just 3 days ago, on March 17th, Oracle officially released Java 26, or JDK 26 as it's technically called. And I'm going to walk you through every single feature in complete detail. Alright, let's start with the big picture. This slide gives us a complete overview of what's actually Java 26. First, look at the left side. If we see three important metrics. Release candidate. This means before March 17th, Java 26 was in its final testing phase. The feature set was frozen, meaning no new features could be added, only bug fixes. 10 total JEPs. JEP stands for JDK Enhancement Proposal. Think of these as official feature requests that go through a rigorous review process. Java 26 has exactly 10 of them. And there are 5 categories. These JEPs are spread across 5 different areas of Java. So let's understand the categories. The core library. This is about the fundamental Java APIs you use every day. Things like collections, networking, concurrency, etc. Java 26 has 5 JEPs in this category. Hotspot. This is Java's virtual machine, the engine that actually runs your code. Hotspot is responsible for garbage collection, cleaning up unused memory, just-in-time compilation, making your code faster, and memory management. Java 26 has two hotspot improvements. Language. This category includes changes to Java language syntax itself. The actually words Next category is language. This category includes changes to Java language syntax itself, the actual words and symbols you write in your Java code. Java 26 has one language JEP. Security. Security features protect your applications from vulnerabilities. Java 26 has one security JEP. And then last is the client library. Last is client library. This historically included desktop UI frameworks like Swing, Applets, etc. Java 26 has one client JEP. On the right side of the slide, you can see all the 10 JEPs listed with their color-coded category badges. We will discuss them in detail. Let's start with the first JEP 500, and it is titled as Prepare to Make Final Mean Final. And this is all about security and predictability. So let's understand the problem. First, let me explain what final means in Java. When you declare a field as final, you are making a promise. This value will never change after it's initialized. It's like setting something in stone. For example, imagine you have a class called box and it has a final field called value. Once you put something in that box, it should stay there forever. That's what final is supposed to guarantee. But here is the problem. There has been a sneaky backdoor called deep reflection that allows code to break this promise. Look at the before section on the left hand side of the slide. Here is where the hack happens. We use reflection to grab the value field and force it to be accessible, even though it's a private and final. We change the final value to magic wand, something that should be impossible. We print again and the value has changed. This is dangerous because malicious libraries could change values you thought were immutable, leading to security vulnerabilities and unpredictable behavior. So here is the Java 26 solution. Now look at the after section on the right. In Java 26, when you try to do this, you get a big scary warning. The JVM is now watching for these modifications and alerting you. So at the bottom of the slide, you see the illegal final field mutation flag with 4 options. Allow. It's an old behavior. There were no warnings before Java 26. Next is warn. Show a warning for the first time. It is by default in Java 26. Next is debug. It shows a warning every time for finding all the violations. And deny, it throws an exception and block it completely so that we are future default. So why this matters? So there are two big benefits here. First is security. Your immutable objects stay immutable, preventing tampering. Second is performance. When the JVM knows a field is truly final, it can apply constant folding, a powerful optimization where it replaces the variable with its actual value at compile time, making your code faster. So if you are using reflection to modify final fields, common in testing frameworks like Mockito, you need to update your code to avoid this pattern, or use the enable final field mutation flag explicitly for specific modules. In a future Java version, probably Java 28 or 29, the deny mode will become default, so start preparing now. Alright, JEP 516 is about making your Java application startup blazingly fast, and it works with any garbage collector now. Let me explain this step by step. So when you start a Java application, several things happen. The JVM loads hundreds of thousands of classes from .jar files. It links them together, connecting references between the classes. It initializes static fields and runs static initializers. The garbage collector sets up its memory regions. All of this takes time, sometimes several seconds for large applications. This is called the cold start problem. So what is AOT? AOT stands for ahead of time. Instead of doing all this work every single time you start your app, you do it once, save the results to a file, and then reuse that file later. It's like meal prepping on Sunday so you don't have to cook every day of the week. So Java 24 introduced this feature, but it had a major limitation. It only worked with certain garbage collectors like G1, serial GC, and parallel GC. Why? Because the cache file stored objects in the exact memory format that those GCs use. ZGC uses a different format, so it couldn't read the cache. Now look at the left hand side of the slide under how it works. Java 26 introduces a streamable format. Instead of storing objects in GC specific format, objects are stored with index numbers. When you load the cache, Java streams these objects into the heap, converting them to whatever format your chosen GC needs. It's like saving a document in a universal format, for example PDF, instead of a specific program format, example Microsoft Word. At the right side showing the commands. Here is how you actually use this. So the first step is training run. You run your application normally, but with these flags. Record training tells Java, pay attention to what classes I am loading. Training data file is save the information to this file. You exercise your application, click around, hit your main features, so Java sees what you actually use. The second step is building the cache. Now you run the application again, but this time Java loads using the training data. It saves the fully loaded state to app.aot. The next step is fast startup. So every future startup, Java loads the cache and it's super fast. Notice you can use any garbage collector now. So what's the real world impact? 30 to 42% faster startup in benchmarks. Cross GC compatibility. Build once, use anywhere. And no code changes. This is purely a JVM feature. So when to use this? This is for microservices that need to start quickly. Serverless functions with cold start penalties. Desktop applications where startup time matters. Any app that starts stops frequently. So the important note is the cache is architecture specific, different for Windows, Linux, etc. You typically build the cache as part of your deployment process and ships it alongside your application. JP 517, HTTP3 support. This is super exciting for anyone building web services or applications that communicate over the internet. First, let me give you some context. HTTP is the protocol browsers and server use to communicate. So what makes HTTP3 special? HTTP3 uses something called quick UDP connections. So it has faster connection establishment, one round trip instead of multiple handshakes. It has better loss recovery. If one packet is lost, others keep flowing, unlike TCP where everything stops. Connection migration. If you switch from Wi-Fi to cellular, your connection stays alive. And there is improved congestion control, smarter about network conditions. In simple terms, HTTP3 is especially better on mobile networks, high latency connections, and when there is packet loss. So look at the left hand side of the slide. This is how you would make an HTTP request in Java before version 26. So let me explain each part. You create a new HTTP client, build a request to a specific URL, send the request and get a response, converting the body to a string. Check which HTTP version was used. It's HTTP2 by default. But HTTP2 has some limitations. It is head of line blocking at TCP level. It has slower connection establishment. And it is less reliant to packet loss on unstable networks. And it is TCP based transport layer. Look at the right side, the new Java 26 way. The only difference is the line 5, where we specify the version to be HTTP3. This tells Java, I prefer HTTP3, please try to use it. Here is the smart part. If the server doesn't support HTTP3, Java automatically falls back to HTTP2. You don't have to write any error handling or retry logic. The Java handles it transparently. So when you should enable HTTP3? So when you have mobile applications, it's a big improvement on cellular networks. If you have real-time services, lower latency for chat, gaming, live updates, high latency connections, international API calls benefit most. And the modern APIs, if you control both client and server, enable it everywhere. So what are the action items for you? Check if your server support HTTP3. Look for quick support. Update your HTTP client code to request HTTP3. Monitor response.version in your logs to see actual usage. Measure latency improvements with real traffic. The beauty of this feature is it's a one-line change with automatic fallback. Very low risk, potentially high reward. So next is JEP 522. Is all about making Java's default garbage collector faster. This is a free performance boost. No code changes required. So what is G1 GC? First, let's understand G1. G1 stands for Garbage First Garbage Collector. It's been Java's default since Java 9, and it's designed to balance two competing goals: high throughput and low latency. Think of it like a restaurant that wants to serve lots of customers without making anyone wait too long. So how G1 manages your memory? G1 divides your heap into about 2048 regions like a grid. Each region can contain hidden space. New objects will go there. Second, the survivor space. Objects that survived one garbage collection. Third is old generation, where long-lived objects will live. And third is humongous. It is for really big objects. Now here is where it gets technical. When G1 moves an object from one region to another during garbage collection, it needs to update all the references to that object. Scanning the entire heap would be too slow. So the solution would be the card table. This is like an index in a book. It tracks which regions contain references to objects in other regions. When G1 needs to find all the references to an object, it just checks the card table instead of scanning everything. So the problem was write barriers. Every time your application code creates a reference from one object to another, G1 needs to update the card table. It does this using write barriers. These are small pieces of code injected into your application. These write barriers synchronize with the GC optimization thread that's constantly organizing the card table. This synchronization creates overhead, like two people trying to edit the same document and having to take turns. Now the Java 26 solution, dual card tables. Look at the left hand side of the slide showing the new architecture. So the old way was to have one card table, app threads and GC thread both trying to access it, and constant synchronization leads to overhead. And in the new Java 26 way, there will be two card tables. Let's call them primary table and secondary table. While app threads write to primary table, GC optimizes secondary table. When primary table gets messy, swap them. Now app threads write to secondary table, GC optimizes primary table. It's like having two whiteboards. You write on one while someone erases and organizes the other, and then you switch. So what are the performance gains? Look at the metrics on the right side. So the throughput improvement is about 5 to 15% in most workloads. Some applications see even higher gains. Larger heaps benefit more. More regions is equal to more card table activity. And how about the memory cost? Each card table is about 0.2% of your heap size. So with two tables, it's 0.4% native memory. For a 4 GB heap, that's only 16 MB extra. That is negligible. So what are the real world scenarios? This helps most when you have high allocation rates, means you're creating lots of objects quickly. Second is many cross region references. So you have large object graphs. Third is multi-core systems. More threads is equal to more contention for locks. So the best part is you have zero configuration. No flags needed, no code changes, automatic after upgrading to Java 26. Just upgrade from Java 25 to Java 26 and your application automatically gets 5 to 15% more throughput. That's like getting a free CPU upgrade. So the next is JEP 524, easy cryptography with PEM encoding. So what's PEM? You know those that start with begin certificate? That's a PEM format. It's how we store passwords, keys, and security certificates. So the old way, you needed like 15 plus lines of confusing code just to read one encrypted key. So in the new Java 26 way, there will be only 3 lines. That's it. Java now has built-in methods that say decode this PM thing and it just works. And what's the real world impact? Security code becomes way easier to write and maintain. This is still in preview, so use the enable preview flag. Alright, this is one of my favorite features in Java 26, JEP 525, structured concurrency. Fundamentally changes how we write parallel code. This is in its 6th preview, and it's getting really polished. Modern applications need to do multiple things at once. So the old way was to use executor service and completable futures. So the problem with this code is lots of boilerplate code, and if one task fails, other keeps running. You have to manually cancel everything, and it's easy to forget executor.shutdown. And tasks are independent. The code doesn't express that they are related. Now look at the after section. Let me explain this piece by piece. So first you create the scope. The try with parenthesis means this is a try with resources. The scope will automatically close when done. No resource leaks possible. The joiner defines the success policy. Any successful or throw means if all tasks succeed, return all the results, and if any task fails, throw that exception. Importantly, if one fails, cancel all others immediately. Config.with timeout is new in Java 26. It sets a timeout. If 2 seconds pass, cancel everything and throw a timeout exception. Fork starts a task on a virtual thread and it's super lightweight. It returns a task object immediately. You don't have to wait. Think of it like launching the 3 rockets simultaneously. Scope.join line blocks until all the tasks complete successfully or one task fails or the timeout expires. So let's understand the joiners. The joiner is like a referee that decides what success means. So Java 26 provides these joiners. So first is any successful or throw. Need all tasks to succeed. Second is await all successful or throw. Same but collect results into a list. Third is await all. It waits for all even if some fail. The fourth is all until. It's a predicate. So it stops when a condition is met. So what's new in Java 6th preview? So Java 26 adds several improvements. So first is on time hook. You can customize timeout handling. Second is better return types. All successful or throw now returns a list of results directly. No more dealing with the stream of tasks. Third is refined naming. Any successful result or throw simplified to any successful or throw. More consistent across the API. So what are the real world examples? Imagine building a dashboard that loads user profile, recent orders, recommendations, account balance, notifications. With structured concurrency, all load in parallel. If any fails, show an error immediately. 5-second timeout for the whole dashboard and it's clean and readable code. Now we are moving to JEP 526, lazy constants. This was called stable values in Java 25, but they renamed it because lazy constants better describes what it actually does. So what's the lazy initialization problem? Let me set up a common scenario. Imagine you have a settings object that loads configuration from a database. Loading it takes 2 seconds. You have 3 options. Eager initialization. Load it when the class loads. But the problem with this is your app start is now 2 seconds slower even if you never use the settings. Second is simple lazy. Load it first time you need it. What's the problem? Not thread safe. Two threads might both try to load it simultaneously, wasting resources and potentially causing corruption. The third is thread safe lazy. Use complex patterns like double checked locking. So the problem is super easy to get wrong. So what was the old way? It was to use double checked locking. So why the double check? First check avoids locking after initialization. Second check prevents multi-threads from loading simultaneously. And why volatile? Without it, one thread might see a partially constructed settings object. This is related to Java memory model and it's very tricky stuff. So the new way is lazy constants. Now look at the after section on the right. You create a lazy constant that wraps the loading function. Load is a method reference. It's like saying call this method when needed. Lazy constant.off is the factory method and you use the get method to retrieve the value. So the first call executes load method and stores the result. Subsequent calls return the stored value instantly. And it's thread safe, guaranteed by the JVM, no locks needed in your code. After initialization, the JVM treats this as a true constant. It applies constant folding optimization, making access as fast as a regular final field. You can also create lists and maps as a lazy constants. You can also create lazy lists and lazy maps. The next is vector API. So what's this about? Modern CPUs can do math on multiple numbers simultaneously using SIMD instructions. Think of it like processing an entire row in Excel at once instead of cell by cell. So what's the problem? Regular Java can't easily use these CPU features. So what's the solution? The vector API lets you write code that automatically use SIMD when possible, giving you massive speed boosts for math heavy operations like machine learning, graphics, or data processing. So it is still in incubator waiting for Project Valhalla features. Use add modules JDK incubator vector to try it. Next is primitive types in patterns and switch. This is the fourth preview, which means it's getting very close to finalization. Traditionally, Java's switch statement was very limited with primitives. So it allowed only certain types like byte short, char, int, not long, float, double, and boolean. It only do exact matches. You could only compare against specific constants. And there were no patterns, couldn't use complex conditions. So in Java 26, you can now use patterns and ranges. You can even ask, does this double value fit in a byte? Java will tell you. So what's the real world impact? It's more expressive, cleaner code for handling numerical values, but is still in preview. So next is JEP 504 and other cleanups. So it's a quick fire round of smaller improvements. So first is applet API is removed. That ancient web plugin tech from the 90s, finally gone. Second is thread.stop method is removed. A dangerous method that's been deprecated since 1998 is now physically deleted. The third is dark mode for JavaDoc. Your API documentation can now match your IDE's dark theme. So the fourth is smaller initial heap. Apps start faster by not grabbing tons of memory upfront. The fifth is file streaming in HttpClient. Upload huge files without loading them entirely into memory. Sixth is Unicode 17.0. Support for the latest emojis and characters. These are quality of life improvements that make Java cleaner and more modern. Alright, so what should you do about Java 26? If you're starting a new project, try out structured concurrency for parallel tasks. Use lazy constants instead of complex initialization patterns. Enable HTTP3 for your API calls. If you are upgrading an existing app, then you need to scan your code for reflection that modifies final fields. Test with the warnings flags first. Consider training an AOT cache for faster startup. Replace old PEM parsing code with a new API. Build the flags you will need. Enable preview for JEPs 524, 525, 526 and 530. Add modules JDK incubator vector for vector API. The good news is most apps will run fine on Java 26 with zero changes. The new features are opt-in. And that's Java 26. 10 features that make your code more secure, faster and easy to write. Which feature are you most excited about? Let me know in the comments, and if you learned something today, smash that like button and subscribe for more Java content.